The fastest object humanity has ever launched into space is moving at about 17 kilometers per second relative to the Sun. At that speed, it would still take more than 70,000 years to cross the gap to the nearest star beyond our own. That single number captures the entire problem of interstellar travel. Our chemical rockets are extraordinary machines, but they are nowhere close to fast enough. And simply building bigger rockets does not solve the problem, because carrying more fuel means carrying more mass, which means needing even more fuel just to move that fuel. This is the same wall that has stopped every serious proposal for reaching another star system since the beginning of the space age. It helps to put that 70,000-year figure in perspective. Light itself, the fastest thing in the universe, takes about 4.24 years to make the same journey to Proxima Centauri, the nearest star to our Sun. A spacecraft would need to travel at a meaningful fraction of the speed of light, not just a small multiple of what our best rockets can currently achieve, to make that crossing within a human lifetime. For comparison, the fastest spacecraft ever built, a solar probe that dove extremely close to the Sun and used its gravity for a tremendous speed boost, reached just under 200 kilometers per second at its peak, an extraordinary achievement by current engineering standards, and still only about 0.07% of the speed of light, closing that enormous remaining gap from a fraction of 1% of light speed to something approaching 10 or 20%. Is not simply a matter of building a slightly more powerful version of an existing rocket. It requires an entirely different category of propulsion, one capable of delivering far more energy per unit of spacecraft mass than chemical combustion can ever provide. For decades, physicists have circled around a small number of possible solutions. You could build something that doesn't need to carry its own fuel at all, harvesting energy from outside the spacecraft instead. You could find some exotic shortcut through space and time that current physics doesn't strictly forbid but has never been demonstrated. Or you could accept that a journey to another star might simply take centuries and design a vessel meant to carry generations rather than individuals. Each path has its champions, and each has run into the same recurring obstacle. The energy required to reach a meaningful fraction of the speed of light is staggering, and the engineering needed to survive and control that energy is harder still. In the middle of this landscape sits an idea that initially sounds almost too simple to work, and yet is now being seriously discussed in peer-reviewed astrophysics literature. Instead of building enormous laser arrays or exotic engines, what if you used nothing more than ordinary sunlight, a spinning system of thin, reflective material, and several years of patience? The concept is called TARS, an acronym for Torqued Accelerator Using Radiation from the Sun, and it represents an attempt to find a cheaper, more physically grounded alternative to the most famous interstellar proposal of the last decade. To understand why this matters, it helps to look at how far the conversation about interstellar travel has actually come, and how far it still has to go. For most of the 20th century, interstellar flight belonged almost entirely to science fiction. Engineers who worked on it seriously were a tiny minority, tucked away in obscure papers and government think tanks. That began to shift in the 1950s and 60s with Project Orion, a real proposal to propel a spacecraft using a sequence of small nuclear detonations behind a pusher plate. On paper, Orion could have reached several percent of the speed of light, fast enough to reach a nearby star system within a human lifetime. It was abandoned for reasons that had less to do with physics and more to do with politics, fallout concerns, and the 1963 Partial Test Ban Treaty, which prohibited nuclear explosions in space. In the 1970s, the British Interplanetary Society picked up the thread with Project Daedalus, a theoretical starship powered by nuclear fusion pellets ignited by electron beams. Daedalus was never meant to be built with the technology of its time, but it served an important purpose. It proved that a self-consistent, physically plausible design for an interstellar probe could be drawn up using known physics, even if the engineering details remained far beyond reach. Variants of this idea continue to this day under names like Project Icarus, an attempt by a later generation of engineers to revisit and improve the original Daedalus design using updated science. Then, in 1996, NASA created something called the Breakthrough Propulsion Physics Project, an initiative specifically intended to investigate speculative but not yet ruled out physics, including concepts like warp drives and wormhole-based travel. For a brief window, this gave legitimacy to the wilder edges of propulsion theory. The project was shut down a few years later, a casualty of budget pressure and the difficulty of producing measurable progress on ideas that remained, by definition, almost entirely theoretical. The interstellar conversation went quiet for about a decade and a half, until 2016, when a very different kind of proposal reignited public interest, this time backed by serious money and a far more conservative approach to physics. In 2016, the venture capitalist and physicist Yuri Milner announced a $100 million research initiative called Breakthrough. The idea behind it was deceptively simple, even if the engineering was anything but. Rather than trying to accelerate a heavy spacecraft, Starshot proposed sending something almost absurdly small, a microchip-sized probe, just a few grams in mass, attached to an ultra-thin reflective sail only a few meters across. The logic here is rooted in basic physics. The amount of force needed to accelerate an object is proportional to its mass. Shrink the mass down far enough, and you no longer need an enormous amount of force to reach extraordinary speeds. The challenge was how to apply that force. Sunlight alone, even though it constantly pushes on any reflective surface through radiation pressure, is too weak and too diffuse to push a sail to any significant fraction of light speed using natural starlight at interplanetary distances. So the Starshot team proposed building a ground-based array of lasers with a combined output on the order of 100 billion watts, to be fired at the sail in a single intense pulse lasting only a few minutes. In that brief window, the sail would be pushed to roughly 20% of the speed of light, fast enough to reach the Alpha Centauri system, our nearest stellar neighbor, in a little over 20 years rather than tens of thousands. Alpha Centauri is not a single star, but a system of two sun-like stars, Alpha Centauri A and Alpha Centauri B, locked in a close mutual orbit, accompanied by a much smaller, dimmer red dwarf called Proxima Centauri, which, at a distance of roughly 4.24 light-years, happens to be the single closest star to our own Sun. In 2016, astronomers using the European Southern Observatory's telescopes in Chile announced the discovery of a planet orbiting Proxima Centauri, now known as Proxima Centauri b/N, with a mass roughly comparable to Earth's and an orbit that places it within its star's habitable zone. The range of distances where liquid water could plausibly exist on a rocky surface. A second, more massive planet, Proxima Centauri c, was identified a few years later, and additional planet candidates around both Alpha Centauri A and Alpha Centauri b have been proposed. Though confirming planets around close binary stars is observationally difficult, since the star's own brightness and gravitational interactions complicate the detection methods astronomers typically rely on. This combination, the single nearest star system to our own, hosting at least one rocky planet sitting in a potentially habitable orbit, is precisely why Alpha Centauri has become the default target for nearly every serious interstellar mission proposal, from breakthrough starshot through TARS and beyond. It is, quite simply, the closest plausible place to actually go and look. This is an extraordinary engineering vision, and the panel of scientists Milner assembled to evaluate it included some of the most respected names in physics and cosmology of the era. Among them, Stephen Hawking and the astronomer Royal Martin Rees, along with the physicist Freeman Dyson, well known for his own speculative work on advanced civilizations and energy-harvesting megastructures. Their conclusion was that nothing in known physics ruled the concept out. The problem, as it so often is with interstellar travel, was not whether the physics worked. It was whether anyone could actually build the thing. Almost a decade on, the difficulties have become clearer. Constructing a coherent laser array capable of delivering 100 billion watts in a tightly focused beam, accurately tracking a sail receding at a meaningful fraction of light speed, and keeping that sail from tearing apart or vaporizing under the heat of the beam are all, individually, enormous unsolved engineering problems. There is also a less technical but equally serious obstacle. A ground-based laser array, powerful enough to accelerate a sail to relativistic speeds, is, by definition, also powerful enough to function as a directed energy weapon, capable of disabling satellites or worse. In an era of renewed great power, tension, and tightening national budgets for basic science, building something that doubles as a potential weapon of mass destruction is politically fraught, even before considering the raw cost of generating and focusing that much power in the first place. None of this means Starshot's underlying physics is wrong. Sails pushed by light remain one of the most promising approaches we have, because unlike a rocket, a sail does not need to carry its own propellant. The energy comes from outside the vehicle. The trouble is entirely in how that energy gets delivered. And it was precisely this bottleneck, the cost and danger of building a giant laser, that led researchers to ask a different question. Is there a way to get a similarly small payload up to a useful fraction of light speed using only the energy the sun already provides for free? No lasers required at all. Propulsion was not the only direction researchers explored while looking for cheaper alternatives to a giant laser array. A separate but related line of thinking focused not on physically sending a probe to another star, but on building a vastly more powerful telescope here at home. One capable of directly imaging surface detail on planets around other stars, without traveling anywhere near them at all. This idea relies on an effect predicted by Einstein's general theory of relativity, gravitational lensing, in which a massive object bends and focuses light passing near it. In much the same way an ordinary/glass lens bends light to form an image. The sun itself is massive enough to act as a gravitational lens, and light from a sufficiently distant source passing close to the sun gets focused to a point far on the opposite side, roughly 550 astronomical units away, more than 13 times farther from the sun than Pluto's average distance. A telescope placed precisely at that focal point would receive light amplified by an enormous factor, potentially turning an instrument of fairly modest size into something with the resolving power of a telescope the size of the sun itself. In principle, sharp enough to make out countenance, weather patterns, or even seasonal vegetation changes on the surface of an exoplanet many light years away. This concept, generally referred to as a solar gravitational lens telescope, has been studied seriously by mission designers for years, precisely because no other proposed observational method comes remotely close to matching its theoretical resolving power for imaging distant worlds. The catch, unsurprisingly, is the same one that haunts every interstellar proposal: getting there. 550 astronomical units is an enormous distance, and beyond simply reaching it, a spacecraft would need to decelerate and hold a precise position at the correct focal point, carry an antenna large enough to transmit detailed image data back across that vast gap, and sustain power generation for what could plausibly be a multi-decade mission duration, possibly even approaching a full century once travel time, observation time, and data transmission delays are all accounted for. Despite its extraordinary scientific potential, the cost and timeline required have so far kept the solar gravitational lens telescope firmly in the realm of long-range proposal rather than funded mission. This difficulty inspired a more modest, Earth-based alternative. Rather than relying on the sun's gravity to bend light, this scaled-down version proposes using Earth's own atmosphere as a refractive lens instead. Since light passing through the graduated density of our atmosphere bends in a predictable way, an effect already familiar from how the setting sun appears slightly flattened and distorted near the horizon, dubbed the terrascope. This concept calculates that Earth's atmosphere could provide a magnification factor on the order of 22,000 times for a telescope roughly 1 meter across, effectively transforming a modest 1-meter instrument into the observational equivalent of a telescope around 150 meters in diameter. Unlike the solar gravitational lens concept, this effect can be exploited from Earth orbit, requiring no multi-decade journey to the outer solar system at all. Both of these ideas, the solar gravitational lens and its scaled-down terrascope cousin, illustrate a recurring pattern in the search for cheaper paths toward studying or reaching other star systems. When an idea like breakthrough starshot runs into a wall of cost and engineering difficulty, researchers do not simply abandon the underlying goal. They look for a fundamentally different physical mechanism, often one hiding in plain sight. that might achieve a similar result through a cheaper and more accessible route. It was exactly this same instinct, searching for an alternative path to the same destination Starshot was aiming for, that eventually led to the propulsion concept at the center of this story. To understand that concept, it helps to first understand exactly why an ordinary solar sail, on its own, runs into a hard physical limit long before it gets anywhere close to relativistic speed. A solar sail works on a simple principle. Photons, the particles of light, carry momentum even though they have no mass. When light reflects off a surface, it transfers some of that momentum to the surface, producing a tiny but continuous push. At a distance of 1 astronomical unit from the Sun, which is the distance from the Sun to the Earth, sunlight delivers a little under 1.5 kilowatts of power per square meter. Spread that energy across a large, ultra-lightweight sail, and the resulting force, though faint, can add up to meaningful acceleration over time. Since, unlike a rocket burning fuel for a few minutes, a sail can keep accelerating for as long as it remains illuminated. If you could somehow hold that 1.5 kilowatt per square meter pressure constant indefinitely, calculations suggest you could, in principle, accelerate a Starshot-style sail up to around 10% of the speed of light within about 20 years using sunlight alone. That is a striking number, and on the surface, it suggests sunlight might be a viable substitute for a giant laser array. The catch is in that phrase, held constant. A free-floating sail accelerating away from the Sun does not experience constant sunlight. As it moves further from the Sun, the intensity of sunlight falls off with the square of the distance, a relationship known as the inverse square law. Double your distance from the Sun, and the available power drops to 1/4. Increase your distance tenfold, and the power available falls to 1/100th. This means a sail starting near the Sun and drifting outward loses thrust very quickly. The mathematics works out so that even given infinite time, a sail relying purely on sunlight pressure while drifting away from the Sun can never exceed about 0.04% of the speed of light, a tiny fraction of what would be needed for a useful interstellar mission. The sail simply runs out of usable light long before it builds up meaningful speed. This is the central weakness that the Starshot team solved by replacing diffuse natural sunlight with a tightly focused, artificially intense laser beam that does not weaken with distance the same way ordinary starlight does. At least not over the comparatively short acceleration phase involved. But there is another way to solve the same problem, one that does not require building a laser at all. If the issue is that a sail loses access to strong sunlight as it drifts away from the Sun, what if, instead of letting it drift, you kept it parked at a fixed, favorable distance from the Sun for an extended period, allowing it to continuously soak up solar energy and store that energy mechanically, before releasing it all at once in a single burst? In other words, rather than trying to ride sunlight directly out toward another star, you could use sunlight to slowly charge up something like a mechanical battery, and only let the payload go once that battery had been charged to its maximum. This is precisely the conceptual leap that leads to the idea of a solar-powered flywheel in space. And it draws on an engineering concept that already exists in a far more mundane setting, much closer to home. A flywheel is at its core a mechanical battery. Energy goes in as a force that spins a mass. That mass keeps spinning because of its own momentum, and the stored rotational energy can later be extracted or released. Flywheels are not exotic technology. Many cars use small ones as part of their engines, and NASA has experimented with high-performance versions, including a unit called the G2 wheel, capable of storing close to 2 million joules of energy in its spin. If a flywheel can store mechanical energy on Earth, the question becomes whether a similar principle could be applied in space, using sunlight itself as the input rather than an electric motor. Picture two thin, identical sheets of material floating in space, both facing the sun, connected by some kind of tether running between them. Now suppose one side of each sheet is coded to be highly reflective, almost mirror-like, while the other side is coded to be dark and absorbent. Critically, the two sheets are oriented in opposite phases relative to each other, so that as sunlight strikes the system, the reflective side of one sheet faces the sun, while the dark side of the other does, and vice versa as the structure rotates. Both surfaces feel an outward push from sunlight because both reflect or absorb photons and therefore receive momentum from them. But a reflective surface receives roughly twice the force of an absorptive one because reflected light bounces back the way it came, transferring momentum in both the absorption and the re-emission, whereas an absorbed photon only transfers its momentum once before being converted to heat and radiated away in random directions, because one sheet at any given moment presents its reflective face to the sun, while the other presents its absorptive face. There is a continuous imbalance in the push each side receives. That imbalance generates a steady torque, a twisting force, and the entire system begins to spin, gaining angular momentum continuously as long as it remains in sunlight. This is, in essence, a mechanical battery being charged directly by the sun. If this setup sounds familiar, it is because a much smaller scale version of the same physics already exists as a popular science toy called a Crookes radiometer, a small glass bulb containing vanes that are silver on one side and black on the other, mounted on a low-friction spindle. Shine a light on it. Interestingly, the toy version actually spins in the opposite direction you would predict from radiation pressure alone, because at the low vacuum pressures typically used inside these bulbs, the dominant effect is not photon momentum, but residual gas molecules, heating unevenly against the dark and light surfaces and pushing the vanes around through thermal effects rather than direct light pressure in the near-perfect vacuum of deep space. However, there is no residual gas to interfere, and the radiation pressure effect would dominate exactly as the simple physics predicts. There is, however, an obvious problem with this design as described so far. If both sides of the system are experiencing a net outward push from sunlight, in addition to spinning, the entire structure would also be slowly pushed away from the sun, just like an ordinary solar sail, drifting outward and eventually losing access to strong sunlight in exactly the same way a simple sail does. Something has to stop that outward drift in order to keep the system parked in a favorable position to keep gathering energy for an extended period. The solution to this problem comes from an unrelated concept first proposed years earlier, originally for an entirely different purpose. to understand the solution. It helps to first understand two related but distinct concepts in orbital mechanics: the statite and a newer idea, sometimes called the quasit. A statite, short for static satellite, is a theoretical object so thin and so reflective that the outward push of sunlight on it exactly balances the inward pull of the sun's gravity. Because these two forces cancel out perfectly, a statite does not need to orbit at all in the traditional sense. It can simply hover in place relative to the sun, neither falling inward nor drifting outward, suspended entirely by the balance between gravity and radiation pressure. This is different from how every planet and ordinary satellite stays in position. Planets are not balanced against gravity. They are constantly falling toward the sun, but moving sideways fast enough that they perpetually miss it, tracing out the closed curve we call an orbit. A statite, by contrast, achieves stability without needing that sideways velocity at all, because the light pressure does the work that orbital motion normally does. A quasit blends these two stability mechanisms together. Rather than being thin and reflective enough to fully cancel gravity the way a true statite would, a quasit is only partially balanced. The outward push from sunlight is real and significant, but it falls short of completely canceling the sun's gravitational pull. To remain stable, a quasit therefore needs some additional tangential velocity, some sideways motion to make up the difference and keep it from spiraling inward. Because part of the work of resisting gravity is already being done by radiation pressure, a quasit can maintain a stable position while moving more slowly than ordinary orbital mechanics would otherwise require at that distance from the sun. In other words, it appears to violate Kepler's laws of planetary motion, not because it actually breaks any physical law, but because the radiation pressure is quietly doing part of the job that orbital speed usually has to do alone. This concept turns out to be exactly what is needed to stabilize the rotating, sunlight-charged flywheel described earlier. By designing the reflective and absorptive coatings so that the system's net radiation pressure does not fully cancel gravity, but instead leaves it in a partially balanced state, the structure can be placed into a quasit orbit, given just the right amount of tangential velocity, slower than a conventional circular orbit at that distance would require. The entire spinning system remains stable in space for as long as needed, continuously charging itself with rotational energy from sunlight, without drifting away from the sun and without needing any propellant to maintain its position, with a stable, continuously spinning system established. The final piece of the design puzzle is how to actually extract the energy that has been slowly accumulating, and how to convert that stored rotational energy into a useful burst of linear speed for a payload heading toward another star. The answer borrows the same trick used by breakthrough starshot, but applies it in a completely different way. Instead of attaching the microchip-sized payload to the sail itself and pushing it directly with light or lasers, the chip is instead attached to the very tip of the spinning structure, connected by the tether that links the two halves of the system together. As the structure spins faster and faster, energy continuously added by sunlight pressure, the centrifugal force acting on that tether grows as well, increasing with the square of the rotation speed. Eventually, the structure reaches a critical spin rate where the tension in the tether approaches the material's breaking point. Just before that limit is reached, the payload is released. At the moment of release, the chip is no longer simply drifting with whatever velocity the overall system has as it orbits the Sun. It carries the full tangential velocity of the spin itself, on top of the orbital velocity of the structure as a whole. If the spin velocity is high enough, when added to the orbital motion, the combined speed can exceed the Sun's escape velocity at that distance, sending the payload not into a new orbit, but outward, permanently, on a trajectory leaving the solar system entirely. In effect, years of slowly accumulated sunlight, stored as rotational energy, get converted in a fraction of a second into a single outward kick, flinging a tiny probe toward interstellar space using nothing more than a carefully engineered piece of reflective material and the light the Sun already provides for free. This concept needed a name, and the researchers behind it settled on TARS, an acronym for Torqued Accelerator, using radiation from the Sun. The choice was a deliberate nod to a particular robot character from a well-known science fiction film about interstellar exploration, one built around the same themes of long voyages, rotating spacecraft, and the tension between ambition and the brutal physical limits imposed by gravity and inertia. It is a fitting homage, since the entire concept traces an unusual path from speculative fiction back into testable physics, a film inspired in part by real astrophysics consultants went on to inspire, years later, an actual peer-reviewed engineering proposal. Having established the basic physics, the next challenge was translating an elegant concept into something that could plausibly be built with materials that already exist, rather than relying on hypothetical future technology. The earliest version of this design used to separate sail panels, joined by a simple connecting tether. But this configuration wastes potential. The tether itself contributes mass without contributing any sail area, meaning it adds dead weight without helping to harvest any additional sunlight. A more efficient approach merges the sail and the tether into a single continuous structure, stretching the reflective and absorptive material all the way from one end to the other in the shape of a long ribbon, so that every part of the structure is simultaneously doing two jobs: catching sunlight to maintain the spin, and physically holding the system together against the centrifugal forces trying to tear it apart. Designing the precise shape of that ribbon required moving from pure physics into structural engineering, a discipline that involves its own distinct set of skills. Working with research collaborator Catherine Lampo, an engineering undergraduate at Columbia University, the researchers modeled how tension would be distributed along the ribbon as it spins. The intuitive answer turns out to be correct. Tension is highest near the center of rotation, where the combined pull of both outer halves of the structure converges, and tension drops off steadily as you move toward either end. This means the ribbon does not need to be a uniform rectangle. Instead, the optimal shape is wide and reinforced near the middle, where the most structural stress accumulates, and tapered down to a much narrower profile toward the tips, where comparatively little material is needed to handle the lower stress at that point. Solving for this shape involved breaking the ribbon down into many small segments and balancing the forces acting at each connection point between them, then refining the solution iteratively until it converged on a smooth, continuous profile. The resulting shape is unusual looking, bulging noticeably in the middle and narrowing toward both ends. But every part of that shape is dictated by structural necessity rather than aesthetic choice. There is a second design constraint that is less obvious but equally important, related to which way the structure rotates relative to its own shape. Every rotating rigid body has what physicists call principal axes of rotation, and for a long, thin object, there are generally 3 of these: rotation around the long axis running through the center, rotation around one of the 2 shorter perpendicular axes, and rotation around the other. Stable spinning generally only occurs reliably around the axis, with either the smallest or the largest moment of inertia. Spinning around the intermediate axis, the one in between, is dynamically unstable, a phenomenon sometimes demonstrated by tossing a rectangular object, such as a tennis racket or a smartphone, into the air with a spin around that intermediate axis, and watching it unpredictably flip end over end mid-flight. This effect has even been documented on the International Space Station, where astronauts have shown a spinning bolt tumbling chaotically when set rotating around its intermediate axis in micrography if the TARS ribbon is made too long relative to its width. Its rotation axis can drift into this unstable intermediate regime, putting the entire structure at risk of uncontrolled tumbling rather than smooth, predictable spinning. Avoiding this failure mode places real limits on how the ribbon's overall proportions can be designed, reinforcing why the final shape is not simply a matter of maximizing sail area, but a careful balance between harvesting sunlight, managing structural tension, and preserving stable rotational dynamics with the shape constraints worked out. The researchers turned to a concrete example using materials that already exist today, rather than speculative future materials. They modeled a ribbon roughly 7 meters wide at its broadest point and 63 meters long from tip to tip, with a thickness of only about 2.8 microns, thinner than a human hair. The chosen material was carbon nanotube sheeting, currently the best available option in terms of tensile strength relative to weight, and notably, a material that is already commercially manufactured and can be purchased today, rather than requiring any speculative breakthrough in materials science. One face of the ribbon would be coated with a thin layer of nanostructured silver, only about 10 nanometers thick, to maximize reflectivity, while the opposite face would use a carbon-based coating to maximize light absorption, recreating the reflective and absorptive asymmetry needed to generate continuous spin, despite its considerable length. The entire structure would weigh only about 1.6 kilograms, light enough that launching it would be relatively cheap and straightforward compared to most spacecraft. For transport, the ribbon could be rolled into a compact cylinder for launch, then unfurled gradually once in space, somewhat like unrolling an accordion, with small thrusters or a brief laser pulse used initially to start the spin before sunlight takes over as the primary driver of continued acceleration. Once deployed and stabilized in its quasi-orbit, the structure would begin a slow, multi-year process of spinning up. According to the modeling, it would take roughly 3 years of continuous exposure to sunlight before the ribbon approached its structural breaking point, the point at which centrifugal tension exceeds what the carbon nanotube material can withstand. That critical spin speed works out to about 12.1 kilometers per second at the tip of the ribbon, a limit set entirely by the tensile strength of the chosen material rather than by any limitation in how much energy sunlight can deliver over that span of time. Because the entire structure is parked in a quasi-orbit, it is also moving around the Sun at roughly 28.3 kilometers per second, just slightly slower than Earth's own orbital speed of about 30 kilometers per second. When the payload chip is released at the critical moment, its final velocity combines both the spin speed at the tip of the ribbon and the orbital velocity of the structure as a whole, yielding a total ejection speed of about 40.4 kilometers per second. This figure is significant for a specific reason: the escape velocity needed to break free of the Sun's gravity entirely at that distance from the Sun is approximately 40 kilometers per second. The chip's actual release speed just barely clears that threshold, meaning it does not settle into a new orbit around the Sun, but instead departs the solar system permanently, headed outward into interstellar space. To put that speed in context, it is considerably faster than NASA's Voyager probes, the fastest human-made objects currently leaving the solar system. Yet it achieves this using no nuclear power source, no chemical propellant beyond what is needed for initial deployment, and crucially, no multi-billion-dollar ground-based laser array. The entire system runs on sunlight and patience. Even so, it is worth being honest about where this leaves the dream of true interstellar travel. 40 kilometers per second, while genuinely impressive compared to existing spacecraft, is still only about 0.013% of the speed of light. At that pace, reaching even the nearest star system would take on the order of tens of thousands of years, not meaningfully different in scope from the timelines facing the Voyager probes today. This is nowhere near the 20% of light speed that Breakthrough Starshot was designed to target using its laser array. Achieving genuinely useful interstellar transit times, journeys measured in decades rather than millennia, would require speeds dramatically higher than what a single basic version of this concept can deliver. One way to think about missions at these more modest speeds is as a multi-generational endeavor rather than a single triumphant journey. Researchers have suggested that rather than launching just one probe, multiple TARS systems could be deployed sequentially over time, each releasing its own payload chip along a similar outbound trajectory. Spaced appropriately, these chips could form a daisy chain stretching across interstellar space, relaying data from the leading probe back through each successive chip behind it, addressing one of the most underappreciated challenges of any deep space mission: maintaining communication across distances so vast that direct transmission back to Earth becomes exceedingly difficult, given how rapidly the strength of a radio signal fades with distance. There are also several relatively modest engineering refinements that could meaningfully increase the basic design's final speed without requiring fundamentally new physics. One option exploits something called the Oberth effect, a well-established principle in orbital mechanics where a given burst of energy produces a larger increase in final speed if it is applied while already moving fast, such as near the point of closest approach to the Sun, rather than while moving slowly. By placing the structure into a deliberately eccentric orbit and timing the payload's release to coincide with the point of closest solar approach, rather than relying on a simpler circular quasit orbit. Engineers could meaningfully boost the final ejection speed without changing anything about the underlying spin mechanism. A second avenue for improvement lies in material science rather than orbital mechanics. The current design relies on carbon nanotube sheeting because it is commercially available today. But graphene, a single-layer arrangement of carbon atoms, offers substantially higher tensile strength relative to its weight. If large-scale, high-quality graphene sheets become reliably manufacturable in the future, simply swapping the ribbon material could allow the structure to reach a much higher spin speed before reaching its breaking point, without altering the rest of the design at all. A third option borrows directly from how the Voyager probes themselves achieved part of their own speed. Gravity assists. By timing the payload's outbound trajectory, the chip could steal a portion of those planets' orbital momentum, potentially adding another 10 kilometers per second or more to its final velocity. The same basic technique that has been used successfully by numerous excursive robotic missions exploring the outer solar system since the 1970s. Finally, there is no requirement that the payload chip stop accelerating the moment it is released. If the chip itself retains some form of small sail surface, it could continue gaining additional speed from residual sunlight pressure during its initial outward coast, squeezing out a bit more velocity even after departing the main spinning structure. Combined, these refinements meaningfully improve the basic design's performance, but none of them, even taken together, comes close to bridging the gap toward relativistic travel. To get genuinely closer to that goal, using this same underlying concept required a more creative and considerably more exotic modification to the core physics. That modification starts from a familiar piece of everyday intuition. The Earth's equator is spinning at roughly half a kilometer per second, which sounds fast, yet nothing standing on the equator goes flying off into space. The reason is gravity, which acts as a restoring force, continuously pulling everything on the surface back down against the outward push of centrifugal motion. The structural limit on the Dar's ribbon discussed earlier exists precisely because there is no equivalent restoring force counteracting the tether's centrifugal tension, only the raw tensile strength of the material itself holding things together. The interesting question, then, is whether some kind of artificial restoring force could be introduced into the system, supplementing or even substituting for tensile strength. The proposed solution is to electrically charge the two halves of the spinning structure with opposite polarities, making one end positively charged and the other negatively charged, while carefully insulating the central region to prevent the two charges from simply neutralizing each other. Two opposite electric charges naturally attract one another, and if engineered correctly, that electrostatic attraction can act as an additional inward pulling force, supplementing the structure's tensile strength and allowing the system to resist a higher centrifugal load than the bare material could withstand on its own. In principle, this means the structure could be spun up considerably faster than its purely mechanical breaking point would otherwise allow, without needing access to some exotic super-strong material at all. There is, however, a complication rooted in classical electromagnetism. a pair of opposite charges, separated by some distance, constitutes what physicists call an electric dipole. And when a dipole rotates, it generates a continuously changing electric and magnetic field around itself. According to the equations of electromagnetism worked out by James Clerk Maxwell in the 19th century, any accelerating charge radiates electromagnetic energy outward, and a rotating dipole is, by definition, a system of continuously accelerating charges. In other words, the very same spinning motion this trick is meant to control also causes the system to continuously leak energy away as radiation, a phenomenon closely related to the kind of energy loss seen in certain types of antennas at low spin speeds. This radiative leakage is extremely small and essentially negligible, far smaller than the energy being continuously supplied by sunlight. But as the rotation speed increases, this leakage grows rapidly, and at some point the energy being radiated away as electromagnetic waves becomes large enough to match the energy being delivered by sunlight pressure in the first place. Once that balance point is reached, the system can no longer continue gaining net energy, regardless of how much longer it remains illuminated, because energy lost to radiation now exactly cancels energy gained from light pressure. This effectively sets a brand new terminal spin speed, one no longer limited by tensile strength at all, but instead by the point where electromagnetic radiation losses catch up with solar energy input according to the underlying calculations. This new terminal speed comes out to roughly 1,000 kilometers per second, a 100-fold improvement over the purely mechanical version of the design that relies on tensile strength alone. While this remains far short of the 20% of light speed targeted by Breakthrough Starshot's laser approach, it represents approximately 0.3% of the speed of light, a substantial leap in capability achieved purely by combining existing materials with well-established 19th century electromagnetic theory. Rather than requiring any new physics or speculative future technology, it is worth pausing on just how unusual this result is. The very same physical effect that limits the system, electromagnetic radiation from an accelerating charge, is also the mechanism by which the system manages to dramatically outperform its baseline mechanical design. Because the electrostatic attraction it relies on for added strength only exists in the first place because the structure is charged, and charge in motion necessarily radiates. The terminal velocity is not an arbitrary engineering choice, but a direct consequence of balancing two competing physical processes against each other. Energy income from sunlight against energy loss through radiation, a genuinely elegant piece of applied physics. Interestingly, a basic TARS structure does not have to be used exclusively for launching tiny interstellar probes, because the underlying mechanism works by converting solar energy into a rotating system of electric charge. And a rotating charge generates a magnetic field. The same hardware could, in principle, be repurposed for an entirely different application closer to home. Shielding astronauts from radiation, Mars presents a specific and well-documented problem for any long-term human presence. Unlike Earth, Mars lacks a strong global magnetic field, largely because its molten metallic core cooled and solidified billions of years ago, shutting down the internal dynamo process that generates planetary magnetism. Earth's magnetic field deflects the bulk of incoming charged particles from the Sun and from deep space, channeling them toward the poles rather than letting them strike the surface directly. Mars has no equivalent global shield, leaving its surface exposed to significantly higher levels of ionizing radiation than Earth experiences, a serious long-term health concern for any future colonists. A spinning, electrically charged TARS-style structure, generating its own localized magnetic field as a side effect of its rotation, could theoretically be placed in a stationary position relative to the Martian surface, hovering above a planned settlement and projecting an artificial magnetic field downward to deflect a portion of the incoming charged particle radiation, functioning as a kind of localized, artificial magnetosphere. Given how lightweight and inexpensive the basic structure is compared to most spacecraft, multiple units could potentially be deployed to provide overlapping or redundant coverage. An entire small fleet of magnetic shields working in concert rather than relying on a single point of failure. This particular application has not yet been explored in nearly as much depth as the propulsion concept itself within the published research, and represents an area researchers have specifically flagged as worth further investigation rather than a fully worked-out proposal. It does, however, illustrate something important about how scientific ideas tend to develop: a concept built to solve one problem. In this case, getting a small payload moving fast enough to leave the solar system can sometimes turn out to have entirely unanticipated applications in a completely different area, simply because the underlying physics involved, in this case, sunlight converted into rotational and electromagnetic energy, turns out to be useful in more than one context. To fully appreciate how unusual it is that solar sailing has become a serious engineering discipline at all, it helps to look back at how long the underlying physics took to be accepted, let alone tested in practice. The idea that light carries momentum and can therefore exert a measurable pressure on objects it strikes was first predicted theoretically by James Clerk Maxwell in the 1870s as a direct consequence of his equations describing electromagnetism. At the time, the predicted force was so vanishingly small that many physicists doubted it could ever be measured at all, let alone harnessed for anything practical. It took until 1901 for the Russian physicist Pyotr Lebedev to experimentally confirm the existence of radiation pressure, using an extraordinarily delicate torsion balance apparatus suspended in a near vacuum, carefully isolating the measurement from interference caused by residual air currents and uneven heating, the very same kind of thermal effects that cause novelty radiometer toys to spin in the wrong direction. Lebedev's experiment confirmed that light does indeed exert a tiny but real mechanical force, validating Maxwell's prediction and laying the theoretical groundwork for every solar sail concept that followed over the next century. For most of the 20th century, solar sailing remained a topic confined largely to theoretical papers and science fiction. That changed in 2010 when the Japanese Space Agency successfully launched Icarus, short for Interplanetary Kitecraft, accelerated by radiation of the Sun, the first spacecraft to demonstrate solar sail propulsion in deep space rather than merely in theory. Icarus used a sail roughly 14 meters across and proved that radiation pressure could indeed be used to measurably alter a spacecraft's trajectory over time. A genuine milestone, even though the resulting acceleration was extremely modest by any practical standard. A few years later, the Planetary Society, a non-profit organization devoted to space exploration advocacy, successfully tested its own light-sail spacecraft. First, with a brief technology demonstration flight, and later, with a more capable follow-up mission that successfully raised its own orbit using nothing but sunlight pressure on its sail, providing further real-world validation that the basic physics scales reasonably well from laboratory experiments to functioning hardware in orbit. These missions, while modest compared to the ambitions of something like Breakthrough Starshot or TARS, were essential proof that the core technology actually behaves the way theory predicts when tested in the unforgiving environment of actual space, rather than remaining purely a matter of calculation. On paper, it is worth noting that solar sails and radiation pressure also play an underappreciated role in spacecraft we already rely on for entirely different purposes. Mission planners for deep space probes routinely have to account for the small but persistent push of sunlight when calculating long-term trajectories, since even unintended radiation pressure on a probe's body and solar panels can accumulate into meaningful navigational drift over a multi-year mission if left uncorrected. In a sense, every spacecraft that has ever flown through the inner solar system has experienced at least a faint echo of the same physics that TARS is attempting to deliberately exploit at a much larger and more intentional scale to properly judge where a concept like TARS fits into the broader picture. It is worth placing it alongside the other major families of interstellar propulsion that have been seriously studied over the decades, since each represents a fundamentally different strategy for solving the same underlying energy problem: nuclear pulse propulsion. The approach behind the old Project Orion concept works by detonating a sequence of small nuclear devices behind a heavily reinforced pusher plate, with each explosion delivering a sharp mechanical impulse to the spacecraft. In terms of raw theoretical performance, this remains one of the most powerful propulsion concepts ever seriously analyzed, potentially capable of reaching several percent of the speed of light using 1960s-era engineering. Its fatal flaw has never been physics, but politics and safety. Detonating nuclear devices in or near Earth's atmosphere is both environmentally hazardous and prohibited under international treaty, and no version of the concept has ever progressed past theoretical study and small-scale, non-nuclear proof of concept testing. Fusion-based designs, exemplified by Project Daedalus and its modern successor, Project Icarus, attempt to achieve similarly high performance without the political and environmental baggage of detonating fission weapons, by instead igniting small pellets of fusion fuel using electron or laser beams inside a reaction chamber, extracting thrust from the resulting fusion plasma. The core difficulty here is one of pure engineering maturity. Controlled nuclear fusion, capable of producing more energy than it consumes, has only very recently been demonstrated in laboratory conditions on Earth, and scaling that achievement up into a sustained, spacecraft-mounted propulsion system capable of operating continuously for years remains a substantial, unsolved challenge, likely decades away even under optimistic assumptions. Antimatter propulsion concepts sit at the most extreme end of theoretical performance, since the annihilation of matter and antimatter converts essentially all of the involved mass directly into energy, according to Einstein's mass-energy equivalence, making it, gram for gram, the most energy-dense reaction physically possible. The overwhelming obstacle here is production and storage. Antimatter does not occur naturally in any meaningful quantity anywhere in the solar system, and the particle accelerator facilities capable of manufacturing it produce only minuscule amounts at enormous cost and with terrible energy efficiency, while safely storing antimatter long-term, given that it annihilates instantly upon contact with any ordinary matter, remains an unsolved engineering problem in its own right. Beam-powered concepts like breakthrough starshot, discussed earlier, sidestep the need to carry propellant or exotic fuel entirely by pushing a lightweight sail from a stationary, external power source, but trade that advantage for the enormous infrastructure cost, engineering difficulty, and geopolitical sensitivity of building a sufficiently powerful and precisely targeted laser array on Earth or in orbit. Then there are far more speculative ideas, such as theoretical warp drive concepts based on deliberately distorting spacetime itself, first explored mathematically by physicist Miguel Alcubierre in the 1990s. These remain consistent with the equations of general relativity in a narrow technical sense, but require forms of negative energy density that have never been demonstrated to exist in any usable quantity, and may not be physically achievable at all using any known or foreseeable technology. Placing such concepts firmly in the realm of mathematical curiosity rather than engineering roadmap, at least for now, set against this landscape. A concept like TARS occupies a distinctive middle ground. It cannot match the raw theoretical performance ceiling of nuclear pulse propulsion, fusion rockets, or antimatter drives, and it falls well short of the speeds Starshot's laser array was designed to achieve. But unlike all of those approaches, every component of the basic TARS design, the carbon nanotube material, the reflective and absorptive coatings, the underlying orbital mechanics, can be built, tested, and potentially flown using technology that already exists today, without waiting on breakthroughs in fusion confinement, antimatter production, or exotic spacetime physics. In a field where most proposals remain permanently decades away regardless of how much time passes, that distinction carries real weight. It is also worth asking what such a mission would actually be for beyond the achievement of leaving the solar system at all. A tiny chip-sized probe traveling at a few tenths of 1% of the speed of light is not capable of carrying the kind of sophisticated instrumentation found on flagship missions like Voyager or New Horizons. But even a minimal payload, equipped with basic sensors for magnetic fields, charged particle density, and dust composition, could provide direct, in situ measurements of the interstellar medium, the thin, diffuse material that fills the space between star systems. In regions far beyond where Voyager 1 and Voyager 2 currently sit, the interstellar medium is not empty. It carries its own magnetic field structure, a slowly varying density of charged particles, and traces of dust grains, all of which shape how cosmic rays propagate through the galaxy, how stars form from collapsing clouds of gas, and even how our own solar system's protective bubble, called the heliosphere, interacts with the surrounding galactic environment. Direct measurements from multiple probes, spread out along different trajectories through a daisy chain relay system, could help build a genuinely three-dimensional picture of this environment for the first time, rather than relying on the single, narrow trajectories that Voyager 1 and Voyager 2 happened to follow. A faster probe could also, in principle, eventually be aimed toward a specific target rather than simply departing the solar system in a convenient direction. Although the speeds discussed here remain far too slow to reach even the nearest star system within a human lifetime, continued refinement of the underlying concept, particularly the electrically charged dipole enhancement, points toward a long-term trajectory of incremental improvement that could eventually narrow that gap, especially if combined with advances in materials science, such as practical, large-scale graphene manufacturing, that are independently being pursued for entirely unrelated reasons across other industries. There is also a broader scientific value simply in continuing to develop and test cheap, modular building blocks for deep space missions. A structure that is light, inexpensive, requires no onboard propellant for years of continuous operation, and can be mass-produced and launched in batches, represents a fundamentally different philosophy from traditional flagship missions, which are typically large, expensive, one-of-a-kind spacecraft built over the course of a decade or more. If concepts like TARS prove viable even at a small scale, they could open the door to a much higher cadence of deep space missions overall, trading the capability of any single probe for the statistical and scientific advantage of being able to launch many of them. It is important to be clear-eyed about exactly how far along this concept actually is. As of now, TARS exists as a peer-reviewed theoretical proposal, published with detailed mathematical modeling of the spin-up process, the structural shape optimization, and the radiative loss calculations behind the electrically charged variant. What it has not yet undergone is any physical prototype testing, whether in a laboratory vacuum chamber or in actual orbit. Several assumptions baked into the published calculations, including idealized material behavior under sustained mechanical stress over multi-year timescales, the practical challenges of reliably deploying and unfurling a 63-meter-long, ultra-thin ribbon in space without tearing or tangling, and the difficulty of maintaining a stable, precisely controlled electric charge differential across a rotating structure for years at a time, remain open engineering questions that only physical testing can ultimately answer. There is also a meaningful difference between a structure performing correctly in idealized simulation and surviving the genuinely harsh environment of deep space for an extended duration, including exposure to micrometeorite impacts, charged particle bombardment from solar wind, and the thermal cycling that occurs as orientation relative to the sun shifts subtly over a multi-year deployment. Any of these factors could degrade the ribbon's structural integrity or its reflective and absorptive coatings well before it reaches its theoretical breaking point. An issue every previous solar sail mission has had to contend with in some form, and one that any future TARS prototype would need to specifically address through material selection and protective design choices. The researchers behind the concept have been notably candid about these limitations, explicitly framing TARS not as a finished, ready-to-fly mission design, but as a deliberately more grounded and buildable alternative to breakthroughs intended to demonstrate that useful progress toward interstellar capability does not necessarily require waiting for an enormous laser array or some entirely new branch of physics. This kind of incremental, openly acknowledged uncertainty is, in fact, exactly how serious engineering proposals are meant to function. A concept gets published. Other researchers scrutinize the math, identify weaknesses, propose refinements, and over time, through that ordinary process of peer review and replication, a rough idea either gets strengthened into something genuinely flight-ready, or its flaws get exposed clearly enough that the field moves on to better alternatives. Both outcomes represent real scientific progress, even though only one of them results in an actual launched mission. Future research directions, explicitly flagged by the team, include more detailed structural simulations, accounting for material fatigue over multi-year timescales, rather than assuming uniform, ideal behavior throughout. Further development of the electrically charged dipole concept to better quantify exactly how the radiative loss balance shifts under realistic rather than idealized charge distributions, and a more thorough investigation of the proposed Mars magnetic shielding application, which so far remains a comparatively underdeveloped side note rather than a fully worked out engineering proposal in its own right. There is also a deeper, almost philosophical dimension worth considering here, one connected to one of the most persistent open questions in all of astronomy, the Fermi paradox. The apparent contradiction between the high statistical likelihood that intelligent civilizations should exist elsewhere in the galaxy, given the sheer number of stars and planets involved, and the complete absence, so far, of any confirmed evidence that they do. One of the many proposed resolutions to this paradox is that interstellar travel might simply be far harder and far more expensive than science fiction has led us to imagine. Hard enough that even technologically advanced civilizations might struggle to spread meaningfully across the galaxy within any reasonable timescale. Concepts like TARS offer an interesting, if speculative, data point on that question. If a civilization roughly at our own current level of technology, lacking fusion power, antimatter production, or the ability to construct planet-scale laser arrays, can nonetheless devise a method for sending tiny payloads to interstellar speeds using only sunlight, basic materials, science, and patience. It suggests that exploring nearby star systems, even slowly and incrementally, may not require the kind of civilization spanning megaprojects often imagined in discussions of advanced extraterrestrial technology. It raises the possibility that a galaxy could be quietly, gradually seeded with tiny, inexpensive probes by civilizations that never developed dramatically more advanced propulsion than what is described here, simply because they had enough time and enough patience to let sunlight do the work across many individual missions rather than one enormous one. This does not resolve the Fermi paradox, and it would be a significant overstatement to claim otherwise. But it does meaningfully shift the conversation away from assuming interstellar travel necessarily requires civilization, scale energy budgets, or physics beyond our current understanding. toward a more grounded picture in which slow, modest, continuously refined engineering, built from existing materials and well-established physics, might eventually be enough to begin meaningfully exploring beyond our own solar system, one small step and one small probe at a time. This same incremental philosophy mirrors how our broader search for life beyond Earth has actually progressed over the past 3 decades. The first confirmed exoplanet orbiting a sun-like star was detected in 1995, and at the time, even confirming that other stars hosted planets at all represented a landmark achievement. Since then, missions like Kepler and TESS have confirmed thousands of exoplanets, and more recently, the James Webb Space Telescope has begun directly analyzing the atmospheric composition of some of the most promising candidates, searching for chemical signatures that might indicate biological activity. Each of these steps, individually, fell short of definitively answering whether life exists elsewhere. Yet, collectively, they have transformed the question from pure speculation into an active, evidence-driven scientific discipline, a cheap, scalable interstellar probe architecture, even one that only reaches a small fraction of light speed, would represent a similarly incremental but genuinely meaningful next step, this time aimed not at observing distant worlds through a telescope, but at finally sending something tangible out to meet the space between the stars directly. There is also a practical engineering history worth drawing on here. Since deploying large, ultra-thin membranes in space is a problem that other missions have already grappled with, sometimes successfully, and sometimes only after significant difficulty. The James Webb Space Telescope, for instance, relies on a multi-layer sunshield roughly the size of a tennis court, made of an extremely thin reflective material that had to be folded into a compact configuration for launch and then carefully unfurled once in space using a precisely choreographed sequence of motors, pulleys, and release mechanisms. That deployment sequence involved hundreds of individual steps, any one of which, had it failed, could have compromised the entire multi-billion-dollar mission, and engineers spent years rehearsing and testing the process on the ground before trusting it to function correctly. Unsupervised, more than 1 million kilometers from Earth, solar sail missions face an analogous challenge, though typically at a smaller scale. Icarus had to deploy its sail using a combination of centrifugal force from a slow initial spin and small extending booms, while LightSail relied on spring-loaded booms to pull its sail taut from a tightly folded launch configuration. Any TARS-style mission would face a broadly similar deployment problem, needing to reliably unroll a 63-meter-long ribbon from a compact launch cylinder without tearing the ultra-thin material, without tangling the structure, and without inducing unwanted oscillations or instabilities that could compromise the careful balance between rotation, structural tension, and orbital stability the design depends on beyond the initial deployment. A multi-year mission profile introduces additional risks that any flight-ready design would need to specifically engineer around. Micrometeorite impacts, tiny but fast-moving particles of interplanetary dust and debris, pose a genuine hazard to any large, thin surface left in space for extended periods, since even a microscopic impact at typical interplanetary closing speeds carries enough energy to puncture an ultra-thin sail material. For a structure under significant rotational tension. Even a small puncture could potentially propagate into a larger tear, particularly near the high-stress region close to the ribbon's center. Engineers working on long-duration sail missions typically address this risk through some combination of redundant material layering, careful selection of sail thickness to balance mass against punch-through resistance, and accepting a calculated probability of gradual performance degradation over the mission's lifetime, rather than expecting the sail surface to remain perfectly pristine for years on end. Thermal cycling represents another practical concern. As the structure's orientation relative to the sun shifts subtly over a multi-year deployment, different sections of the ribbon will experience varying degrees of heating and cooling, and repeated thermal expansion and contraction can gradually fatigue even strong materials over enough cycles. Carbon nanotube sheeting generally performs well under these kinds of thermal stresses compared to many alternative materials. One of the reasons it was selected for the baseline design in the first place. But a flight-ready version of the concept would still need extensive ground-based thermal cycling tests to confirm that performance holds up under realistic, multi-year mission conditions, rather than just the idealized assumptions used in the initial theoretical modeling. None of these challenges are unique to TARS, and none of them are considered insurmountable by the standards of modern aerospace engineering. They simply represent the ordinary, unglamorous work that stands between a compelling theoretical proposal published in a research paper and an actual functioning spacecraft. That gap, often described informally within the aerospace community as the difference between a concept being merely technically possible and being genuinely flight-ready, has historically taken anywhere from several years to a couple of decades to close for comparable missions, depending on funding, institutional priority, and how many of the underlying assumptions survive contact with real-world testing. It is worth taking a closer look at why carbon nanotubes specifically were chosen for this design, since the choice reflects a genuinely interesting area of modern materials science. Carbon nanotubes are cylindrical structures made of carbon atoms arranged in a repeating hexagonal lattice, essentially a sheet of graphene rolled into a tube only a few nanometers in diameter. Despite their microscopic scale, individual carbon nanotubes exhibit tensile strength dramatically higher than steel when compared on an equal weight basis, a property that comes from the exceptional strength of the carbon-to-carbon bonds within the hexagonal lattice structure itself, combined with the near-total absence of the microscopic defects and impurities that typically weaken bulk materials like metals, translating that extraordinary strength from individual microscopic nanotubes into a large manufacturable sheet has historically been the harder engineering problem, since any large-scale sheet inevitably involves countless individual nanotubes bonded or interwoven together, and the strength of those connections between tubes is generally far weaker than the strength of the tubes themselves. Significant progress has been made on this front over the past 2 decades, with various manufacturing techniques now capable of producing nanotube sheets, sometimes called bucky paper, at commercially available scales. Even if the resulting bulk material still falls considerably short of the theoretical strength of a single, defect-free, This is precisely why the published TARS calculations used realistic, currently achievable carbon nanotube sheet properties, rather than the idealized strength of individual nano. When computing the 12.1 km per second baseline breakup speed discussed earlier, the two-dimensional sheet material that carbon nanotubes are essentially rolled versions of offers a theoretically higher strength-to-weight ratio still, and has been the subject of intense research interest since it was first isolated and characterized in 2004. Work that was recognized with the Nobel Prize in Physics in 2010. The challenge with graphene has always been scaling production from small laboratory samples, often only a few millimeters across, up to the kind of large, continuous, defect-free sheets that a project like TARS would require. An area where steady but incremental progress continues to be made across multiple unrelated industries, from flexible electronics to advanced composites, rather than being driven specifically by aerospace applications. Because TARS does not require any material breakthrough that does not already have strong commercial incentive behind it from these other industries. Any future improvement in large-scale graphene manufacturing achieved for entirely unrelated commercial reasons would likely translate directly into improved TARS performance as a useful side benefit, without requiring dedicated aerospace-specific research funding to drive that particular advance beyond the materials and the physics. There is also a meaningful shift in mission philosophy embedded in a concept like this one, worth examining on its own terms. Traditional deep space missions, from Voyager through Cassini, New Horizons, and the James Webb Space Telescope, follow a broadly similar model: a single, highly capable, extremely expensive spacecraft, built over the better part of a decade by a large team, carrying a diverse suite of scientific instruments, and launched with the expectation that it must function correctly, often for decades. Because there will be no second chance and no opportunity for in-flight repair, this model has produced extraordinary scientific results, but it is also slow, expensive, and inherently risk-averse. Since the enormous cost and multi-year development timeline of any single flagship mission makes mission planners understandably cautious about taking on unnecessary technical risk. A structure like TARS, by contrast, costing a small fraction of a traditional flagship mission and requiring comparatively modest mass to launch, suggests a fundamentally different approach. Rather than building one extremely capable probe, build many simple ones, except that some fraction may fail due to manufacturing defects, deployment problems, or unforeseen environmental hazards, and rely on the statistical reliability of the fleet as a whole rather than the individual reliability of any single unit. This mirrors a broader trend already well underway elsewhere in the space industry, where the historical model of building a small number of extremely expensive, exquisitely engineered satellites has increasingly given way. For many applications, two constellations of cheaper, mass-produced satellites working together, trading individual sophistication for collective redundancy and lower overall cost per unit of capability delivered. Applying that same philosophy to interstellar exploration is a genuinely novel idea, since deep space missions have historically been considered far too expensive and far too technically demanding to ever be produced at any meaningful scale. If a structure can be built for a small fraction of the cost of a traditional planetary probe, weighs little enough to be launched relatively cheaply, and requires no propellant for years of operation. It becomes plausible, at least in principle, to imagine dozens or even hundreds of such units being constructed and deployed over time, dramatically increasing the total scientific return per dollar spent compared to investing that same budget in a single, more capable, but inevitably much more expensive mission. This does not mean flagship missions become unnecessary. The kind of detailed, instrument-rich science delivered by missions like Voyager or New Horizons during their close encounters with planets and moons simply cannot be replicated by a chip-sized payload with minimal onboard instrumentation. But for certain categories of science, particularly broad, distributed measurements of the interstellar medium across many different trajectories and locations simultaneously, a swarm of cheap, simple probes may ultimately deliver more useful data than a single expensive one ever could, simply by virtue of being everywhere at once rather than concentrated along one narrow path. So where does this actually leave us? A concept like TARS will not, on its own, get a human crewed mission to another star system, and it was never intended to. At its current basic level, it offers a way of sending a tiny, instrument-light payload to roughly 40 kilometers per second using nothing but sunlight, careful structural engineering, and several years of patience. A meaningful improvement over existing spacecraft, but still far short of anything resembling rapid interstellar transit. Even its more ambitious electrically enhanced variant, reaching toward 1,000 kilometers per second by exploiting the radiative physics of a rotating charged dipole, remains a small fraction of the speed that would be needed to reach another star system within a human lifetime. What it does offer is something narrower, but still valuable, a physically grounded, buildable today demonstration that meaningful progress toward interstellar capability does not have to wait on a 100 billion watt laser array, a working fusion reactor, manufactured antimatter, or some yet undiscovered branch of physics. It is a reminder that incremental, well-understood engineering, applied carefully and combined in creative ways, can sometimes outperform expectations, not by breaking any rules, but by finding genuinely clever ways to work within them. The honest scientific position is that this remains, for now, a peer-reviewed proposal rather than a flown mission. The mathematics behind the spin-up process, the optimized ribbon shape, and the radiative balance calculations for the charged variant have all been published and subjected to scrutiny by the broader research community, which is exactly the process by which speculative engineering ideas get tested, refined, or ultimately set aside in favor of better alternatives. What comes next, as is true of most early-stage aerospace concepts, depends on a combination of further refinement of the underlying models, dedicated funding to build and test a physical prototype, likely starting with a small-scale, ground-based or low Earth orbit demonstration, well short of a full interstellar mission, and the accumulation of enough confidence from that smaller-scale testing to eventually justify a much larger, full-scale deployment. There are specific open questions that future research will need to address before any of this moves from paper to hardware. How exactly does carbon nanotube sheeting behave under multi-year, continuous centrifugal loading in the thermal and radiation environment of deep space, rather than under the comparatively brief and controlled conditions of a laboratory test. Can a 63-meter ribbon be reliably folded, launched, and unfurled without introducing structural flaws or asymmetries that would destabilize the careful balance between spin, tension, and orbital position the design depends on? How precisely can a stable, sustained electric charge differential actually be maintained across a continuously rotating structure over a period of years? Given the practical challenges of insulation, charge, leakage, and the harsh radiation environment of interplanetary space, and how would a real structure's performance be affected by the inevitable accumulation of micrometeorite damage over a multi-year mission, rather than the idealized, undamaged material assumed in the initial calculations? None of these questions have definitive answers yet, and that is, in a sense, exactly the point. Science at this stage is not about having all the answers. It is about identifying the right questions clearly enough that they can actually be tested. One experiment, one calculation, one small-scale prototype at a time. That is precisely the kind of incremental, patient process this entire concept itself was born from. Not a single brilliant insight, but the accumulation of many smaller ideas: statites, quasats, radiometers, tensile material science, and basic radiation pressure physics, brought together in a new combination because someone took the time to ask whether an existing, more expensive idea could be approached differently. If there is a broader lesson worth carrying away from a story like this one, it might be less about the specific numbers, the 40 kilometers per second, the 12.1 kilometer per second breakup speed, or the 1,000 kilometer per second theoretical ceiling, and more about the underlying approach itself. Big, expensive, headline-grabbing proposals like Breakthrough Starshot tend to dominate public attention, and rightly so, since they represent genuinely ambitious attempts to solve one of the hardest problems in all of engineering. But quieter, more incremental ideas, built from cheaper materials and simpler physics, sitting in the gaps left behind by those larger proposals, sometimes turn out to matter just as much, precisely because they do not require waiting for some distant, future technological breakthrough to begin making real progress. If this kind of careful, physics-grounded approach to one of humanity's oldest ambitions is something you find genuinely interesting, sharing it and following along with where this research goes next helps more people encounter ideas like this. And there is a great deal more groundbreaking research in propulsion, in cosmology, and across the rest of physics, still waiting to be properly explained. The gap between an elegant theoretical concept and a working spacecraft is rarely closed by a single dramatic breakthrough. It is closed, slowly and deliberately, by exactly this kind of patient, peer-reviewed, incremental work. One carefully validated idea building on the next, until eventually, the things that once sounded almost too crazy to work turn out to be exactly the things that did, for now. The chip-sized payload of a future TARS mission remains on paper rather than in space, and the question of whether sunlight, carbon nano, and careful structural engineering can genuinely deliver humanity's first true taste of the space between the stars remains open. But unlike so many of the grander interstellar proposals that came before it, this is one where every piece of the puzzle, the materials, the orbital mechanics, the underlying physics, already exists, waiting only for someone to put it all together and find out.